Hello, in this video we are going to talk about the genetic algorithms. This presentation is based on Daniel Schiffman's book The Nature of Code. As you see, in this book there is a chapter dedicated especially to these algorithms. First, let's talk about the concept of the genetic algorithms. These algorithms deal with problems whose correct answers are significantly fewer in number than the total number of possible answers. Thus, a brute force solution, in other words, by checking all possible answers in search of the correct ones, would take far too long. For example, Bonnie and Clyde are playing a game. Clyde thinks of a number between 1 and 1 billion, and Bonnie has to guess it. A brute force solution would be the following. Bonnie starts from 1 and asks Clyde about each number until she reaches Clyde's number. In this scenario, luck plays an important role, but it is obvious that in the general case, Bonnie will have to count for years until she guesses Clyde's number. For example, if Clyde's number was 23 million, there would be a lot of counting. However, if after each of Bonnie's attempts, Clyde tells her things like "you're close" or "you're very, very close," "now you're far" or "you're very far," and so on, then Bonnie will be able to judge how fit her answer is. Having this information, Bonnie will be able to reach the right answer more easily and quickly by getting closer and closer to it each time. Now let's look at a good example of a problem inspired by a famous paradox that can be solved using a genetic algorithm. This is the infinite monkey paradox. Imagine there is an ever-living and hard-working monkey who randomly presses the keys of a typewriter for an infinite amount of time. It is a famous fact that this monkey will eventually write the Bible. What is more, the monkey will one day write all the texts that exist, and it will even write them infinite number of times. Unfortunately, we do not have an infinite amount of time. Therefore, if you want to write the Bible ourselves, we will need some help from the genetic algorithms. Let's look at the following simplified situation. We want to write just a quote from the Bible. And I chose the quote in the beginning was "word." This is a string of 25 characters, including the spaces. Playing the role of the monkey, we will make random attempts to write the string until we succeed. We will look at the general principles of the genetic algorithms in the context of this example. The genetic algorithms are closely related to Darwin's theory. Three fundamental principles must apply to all genetic algorithms. The first one is heredity. There must be a process in which the children, in other words, our next attempts to write the string, receive information from the parents, in other words, our previous attempts. This information, in our case, will be the characters of the parent strings. Then, its variation. There must be a variety of traits in the population or a means of introducing variation, such as mutation. If we look at a population of organisms which are exactly the same, their children will be completely identical. Thus, a new combination of traits will never appear. In our example, this would mean starting with the same wrong string and trying over and over again with the same ones. That means we will never write the quote we want. And the last one is selection. There must be a mechanism which makes some members of the population able to pass down their information and preventing others from doing so. In the real world, organisms which have better traits are more likely to survive and live a generation. The better genes will be preserved in the generation and the worse ones will be lost. The equivalent of this is in the genetic algorithms is that our next attempts will be more similar to our previous ones that were closer to the desired result, and less similar to the attempts that were further away from it. Let's look at the general plan of a genetic algorithm. First, we start with the initial population. Then we perform a selection and then the reproduction, which has four steps. We choose the parents, Then we have crossover and mutation, and with the new population that we now have, we go back to step number 2. We again perform selection and so on and so forth, and it becomes a cycle. Okay, the first step was initial population. We create a population of n randomly generated strings. In our example, this would mean creating n random strings with 25 characters. Then it's time for selection. We calculate how fit these strings are. For example, for each string in the population, we can count the positions where the characters match with the string we want to write. Thus, if a string has more matching characters, it will be more fit. According to how fit the strings are, we will determine which of them will be more likely to have children and pass down the information, and which ones will be less likely to have children. In other words, fitter strings will have a higher probability to reproduce, and those who are less fit will have a lower probability to do so. For the reproduction, we repeat these 4 steps n times. First, we choose 2 parents according to the probabilities which we have already calculated. For example, these 2 parents over here. Then we perform a crossover. We create a child, that means a new string, which is a combination of the strings of both parents. One way to do that is to cut the strings in an arbitrary point and take the beginning of the first string and the end of the second string. And then the child is born. And then it's time for mutation. According to a predetermined frequency of mutation, we change random symbols from the string of the child with other random symbols. This is the mechanism for adding extra variation. For example, we have changed the symbol O, the capital letter A. And then we add the new child to the new population. Each time we perform all of these 4 steps, we get 1 child. In the beginning we had 8, our population had 8 elements, so we want our new population to have n elements as well. That's why we need to repeat this process n times, because each time we get 1 more child. And then, having the new population, we go back to the beginning. We again perform selection, then reproduction, and then we replace the old population with the new one, the children, and then we go back to the beginning and do the same thing as well. Each new population will be closer and closer to the desired result, the string we want to write. Okay, however, there are other more interesting examples. Let's consider the following situations. First, here is a population of rockets which is fired from a point at the bottom of the screen, and the goal of each one is to reach the black circle at the top. The path of the rockets is a series of movements, and each of them is characterized by 2 things, direction and speed, which are randomly chosen at the beginning. However, all the movements have the same duration. The rockets that reach a point closer to the target are defined as more fit. You can see at the beginning the paths are random, then the rocket over here was way more fit than the other rockets. That's why all of the children in the next generation look like it, because they were its children. Oh my god. Okay. So during the reproduction, 2 parent rockets are chosen and a child is born. This is done by making a random combination of the paths of the parent rockets. For example, the first 2 movements of the child's path will be taken from one of the parents. The next 3 will be taken from the other parent, and so on. Thus, in each succeeding generation, the paths of the rockets become closer and closer to the optimal one, a straight line from the beginning to the black circle. We reached that optimal path only in the 5th generation because it was really simple. But now let's look at the next example. Here the situation is more interesting. an obstacle is introduced. The rockets that collide with it stop moving. And let's see that. At the beginning, the paths are random. Okay. Now we have some changes made to the fitness, to the way we calculate the fitness of the rockets. Now it can't just be how close to the square the rockets are, because a rocket that collides here with the obstacle is closer to the square than a rocket that's, for example, here, and the rockets that are here are actually on the right path. So we will further reduce the fitness, and that way the chances of these rockets being chosen as parents by lowering their fitness level. We lower the fitness level of the rockets which bump in this obstacle. Okay. Now you can see the two groups are formed. One of them is going around the left, and the other one is making a turn here. This is the right path, so and they go closer to the square. That's why the other group the rockets from the other group no longer exist. Okay, they found the right way. Oh, that was a mutation here, the rocket over here. Its path had nothing to do with the other ones. Another thing we can do is to lower the fitness of the rockets which miss the square, because some of them do that. That way, the overall generation will look more like the one that bump directly in the square. And that's it. We have a look at 2 more generations. And here in the third, I think in the 30th generation, we'll have a look at one more mutation over here. Yeah. Okay, so in the end they found the right path to the square. Okay, in conclusion, the genetic algorithms are widely used in computer science, but what is more, they are crucial for solving many physical and ecological problems. This is why their research is an interesting and important task. That's the end of the video, and I chose this picture of a rabbit population to say you goodbye. So I hope you enjoyed the video. We'll see each other in the next one.